all of the other examples in this section had, for the most part, they were products of sines and cosines or secants and tangents, but they had them multiplied together. And you have to remember, two things multiplied together inside an integral is a problem. You cannot, repeat, you cannot just integrate each part if they're multiplied together. Other things you can't do is if something is raised to a power, you can't just integrate inside and ignore the power. There were a few folks that tried that on the most recent test. Integration is messy, and if you have two things multiplied together with x's, or you have something raised to a power that is like a cosine raised to a power, you can't just integrate inside and then keep the power. That doesn't work. It's not the antiderivative. It's the wrong answer. Okay? So we need all these different strategies to help get rid of those powers when they're there, or in the case like we have in this example, two different trig functions multiplied together. Okay? So the nice thing about these is they work when you don't have powers, but you just have a sine times a cosine, or a sine times a sine, or cosine times a cosine. These all will help you turn them into just a sine added to just a sine, or just a cosine subtracted from a cosine, or a cosine added to a cosine. These are what are called the sum and difference formulas from trig. Sum of angle formulas. Notice, and they're also the difference of angle formulas. Technically, they're like a combination of the two, because you got a difference here and you got a sum here. But here's your clue. As a detective trying to solve the integration problem and figure out which technique, if you just have a sine times a cosine, you find these trig identities and it turns it into sine added to sine, cosine minus cosine, or cosine added to cosine. So which one of those would apply in this case? First one, okay? So what's my A? And my B? So according to that first formula, what is sine of 4x times cosine of 5x? Which is negative x, right? This is 4x minus 5x. Plus 9x. Okay? dx. Now, can you do that integral? What would you do first? I would pull the 1/2 out. That's fine. Or distribute it. Either one works. Sine of minus x plus sine of 9x dx. Yes, you can. Now, just integrate them both separately because there's a plus sign between them. Okay? So there's 1/2. So the derivative, so the integral of sine is negative cosine minus cosine of minus x. But remember, if I were to take the derivative of this, I need to end up with a sine of negative x. A positive sine of negative x. Derivative of cosine is negative sine. But you'd also have to multiply by the negative of what's inside. So I have to put an extra minus out here because of that minus inside there. Does that make sense? Why I did that? It's the same reason I'm going to do a 1/9 on the next one. I'm dividing by the thing that the chain rule will contribute, so it'll cancel back out.
So it'll be 1/9 sine?
Plus 1/9, not sine, but cosine 9x. But what's the derivative of cosine's negative sine? So I need a minus there too.
Why are you... Okay.
Because the integral of sine is negative cosine, so that's where the minus comes from. The 1/9 comes so that when I do take the derivative, I have to multiply by the chain rule, and I have to multiply by 9. I need something to cancel it out. Plus C. Minus minus makes plus. So that's one. I'm going to just read this in here. 1/2 cosine of minus x minus 1/18 of cosine of 9x plus c. There's one other identity that's going to come in handy right here. I actually could have used another version of it for sine. The cosine of negative x is cosine of x. Cosine is what's called an even function that minus signs inside can just be thrown away. So I would write my final answer as 1/2 cosine of x minus 1/18 cosine of 9x plus c. But as I was able to get rid of the problem product using these identities up here. Sure would be nice if we had all those identities that we need to use on a single page, wouldn't it?
Yeah.
I think I'm going to stop the recording there because that's the end of that section.